Okay, it's my great pleasure to introduce Farmer Schlutzenberg, who is going to give the talk today. He has a junior professorship at the University of Münster currently, and he is going to speak about non-uniqueness and non-definability of elementary embeddings beyond choice.
Okay, thanks, Günther, and thanks for the invitation, Günther and Vika. And it's very nice to be able to have the opportunity to talk about stuff. Yeah, so this is joint with Gabe Goldberg. Okay, so I can go across that hopefully. So there's a list of references here on things that I refer to in the talk. I'm not going to go through it, but if you need to later, you can see it. Okay, so large cardinals beyond a measurable cardinal are typically exhibited by an elementary embedding from V into some transitive class M. Oh, that's right. I wanted to also add my annotate and this spotlight. So I think, can you see the cursor reasonably here?
Yes, very good. Mm-hmm.
Yep. Okay. Okay, so so we get larger cardinals when we require more similarity, by requiring more similarity between the transitive class M and V. And so Reinhardt suggested taking that to the logical extreme with setting M equal to V. And so we get this notion of a Reinhardt cardinal being the critical point of an elementary embedding from V into itself. And we'll also say here that such an embedding is a Reinhardt embedding. And so, of course, Kuhnen proved that under ZFC that there's no elementary embedding from a V lambda plus 2 into itself. Then it follows easily that that there's no, under choice, that there's no elementary embedding from V into itself. And so I'll just remind you what happens in that second step. We have a, so now this should, click there. So we have an embedding. Oh, now I need to connect this pencil. Okay, so we have an embedding. No, oh, I see. Like this, J from V into V, and so if we take kappa 0 as the critical point of this J, J moves its critical point up to kappa 1, so kappa 1's JF kappa 0, and so on. So kappa 2 is JF kappa 1, and we keep repeating that process, and then take lambda to be the sup. So we can then consider, so then we get J of lambda equals lambda. So looking at the sequence, J of the sequence here of kappa n's, n less than omega. So this is the same sequence except shifted up by 1, so that's kappa n plus 1, n less than omega. And so by elementarity you fix the sup, and so we get J of lambda equals lambda. And so that gives us then, lambda plus 1 and 2 are fixed, and so you get the restriction as an elementary embedding here. In order to execute this argument that we just did using the applying J to this kappa sequence, of course we need to be able to construct the sequence in the first place. So we have to be able to refer to J in separation and collection. And so one way to formalize that, which I'll use in the talk, is as follows. So I write ZF A here being a predicate symbol is just ZF plus collection and separation for formulas in the language where we have membership and this predicate symbol A. And then ZFCA adds choice in. And so if we take ZFJ, J, one of these symbols, there's a natural axiom scheme that asserts that J is an elementary embedding from V into itself. One actually, it suffices just to say that J is sigma 1 elementary by a standard result that actually implies the full elementarity here, because we're also saying that V models ZF. So that's enough. Right, so that's what we actually used in the previous slide. We had ZFCJ here in order to run this argument with the kappa n's and get the embedding V lambda plus 2 into itself. Okay, so the the big open question there is whether ZFJ alone, so without choice, suffices to rule out the embedding from V into itself. So can we do Kuhn's theorem without choice? Okay, so just some notation, the script E of M for M, whatever structure, denotes the set of elementary embeddings from M into itself, and a variant EKM is for sigma K elementary. So I'll sometimes use this notation, sometimes I'll just write the function out itself. Okay, so one basic observation is this theorem, which Suzuki published in 1999, that under ZF, if J is a class which is definable from parameters over V, then J is not a Reinhardt embedding. This notation here is the elementary embeddings from V to V. Of course, actually, now I write, this notation was meant to denote the collection of all such embeddings. So naturally, writing this notation is actually somewhat maybe problematic formally, but I just mean that in this case, we have a class which is definable from parameters, so we can say J is not an elementary embedding. Okay, so under ZF alone, if you restrict your, one standard formulation of ZF is the classes are all of this form. So in that form, naturally, this disproves the Reinhardt cardinal if we restrict to such classes. But the question, as I mentioned, was does ZFJ rule it out? And there, it's a different question. This theorem of Suzuki's here is refined by this other result here for Hamkins, Kermeyer, and Perlmutter, that under ZF, in fact, no elementary embedding from hard into itself is definable from parameters in V. So, naturally, if you've got J V to V elementary, then the restriction to hard is elementary hard to hard. So, Suzuki's theorem is a weaker version of this theorem under here. Yeah. Okay. So, and in particular, as a consequence, if we have J is V into V is elementary, then J restricted to ordinals cannot be definable from parameters. So basically the same thing as, well, anyway, yeah, consequence of this. Okay. So in the talk, I'm going to look at various generalizations of Suzuki's theorem. So there's different directions you can look at attempting to generalize it. The first, the first thing to consider is you can generalize definability. So in particular, you can look at constructability. So however, if we're looking at Suzuki's theorem itself, then we already have all of V, so there's no room left to construct above V. So, I'd want to talk about L of V above there, but, it doesn't make sense literally. So a way to formalize that is to replace V with a rank segment, V lambda, some lambda where maybe we assume that V lambda models ZF, so it looks like what V used to be. So then we can ask whether we can get an elementary J from V lambda into itself, which is constructible from V lambda, so in L of V lambda. And so notice that Suzuki's theorem says Suzuki's theorem applied to V lambda says just that if V lambda models ZF, then J is not in L1 of V lambda. It's the first step of the constructible hierarchy, since the things in L1 of V lambda are exactly the subsets of V lambda, which are definable from parameters. So that's what his theorem rules out. But then, therefore, a natural generalization is to ask what happens when we go into higher levels of L above there. We can also look at higher order. So instead of just constructibility, we can look at higher order more generally. So we can look at if we've got some larger V lambda plus alpha, can we get J? So in this case, J is going to be in there, but we could ask whether J is definable over V lambda plus alpha from some parameter still in V lambda. So that's another way you might generalize the definability. Okay, and then second thing is we can reduce the theory that we're assuming of the V lambda. So, initially with Suzuki's theorem, we have a model of ZF, but you can just get rid of that and take an arbitrary ordinal lambda. So we can, limit or successor ordinal. We can ask whether you can get, we can ask whether we can have Suzuki's theorem. So can J be definable over V lambda from parameters, or could J be constructible in this way but with an arbitrary lambda here? Third, we can reduce elementarity, so look at partially elementary maps instead of fully elementary, but similar questions here. And then aside from definability and so forth, we can also look at uniqueness instead. So we can ask, is J the unique elementary embedding with some property, such as extending some initial segment of itself, so V alpha here, alpha less than somewhere, some V alpha less than lambda. Or maybe is J the unique extension of its restriction to ordinals? So questions like this. There's also questions you can look at where you go to generic extensions and ask, I don't know, all sorts of variants of these questions if you're looking at generic extensions as well. Okay, so I'm going to look at a few of these. The first thing I'll look at is define. So really the number 2 here, reducing ZF and ZFJ. So considering arbitrary ordinals and definability over phi lambda. Okay, so the first basic observation here is the following. So this is an old observation. It's in one of Lever's papers, but I don't know where it was appeared first. But if we have J in E1 V delta plus 1, so this is saying sigma 1 elementary from V delta plus 1 into itself, and delta is a limit ordinal, then J is definable over V delta plus 1 from the parameter P, where P is just the restriction of J to V delta. So in the picture here, so we just have V delta, delta is a limit, and delta plus 1. We can look at this part, J restricted to V delta. That parameter, delta here is a limit ordinal, so that object is actually in V delta plus 1. J restricted V delta is obviously a set of pairs XY, which are in V delta, so this is a subset of V delta. So this thing is a potential parameter. And in fact, it is definable from that, and moreover, it's the unique elementary sigma 1 elementary extension of this restriction. And it's done, in fact, in a canonical way with this canonical extension. So J is equal to the canonical extension of its restriction to V delta, and that's the super plus denotes this extension. And that's easily it's easy to see that. So to see what that should be. So canonical extension, if we have a limit ordinal delta and K is sigma 1 elementary from V delta into itself, then we define the canonical extension of K as just the unique map that could be an elementary embedding from V delta plus 1 into itself if there's going to be one. And that's just given by sort of using K to move all of the pieces of a given set. So, you have, I need to do this. We have V delta plus 1. So the elements V delta plus 1 are all subsets of V delta. So we consider some X here, subset of V delta. J acts already on, K acts already on V delta. So we can move all the restrictions of X down at smaller V alphas here. So it's some V alpha. And then just take the union of them. So we have here, J of X intersect V alpha is some piece down here. So we just let alpha vary over overall ordinals less than delta, move all those pieces across and take the union. So that's what this is doing here. So I'm writing J here, but it should have been K in the diagram.
What is the significance of sigma 1 here?
What do you mean?
Okay, why do you need that it's sigma 1?
Oh yeah, maybe sigma 0 might be enough, but I don't know.
Why do you need any kind of definability in the first place?
In the first.
And any embedding or?
No, well, I mean by sigma 1 elementary, I just mean it's.
I see. It's sigma 1 elementary. Sorry, not sigma 1. Like I misunderstood you. Yeah, thanks.
Okay, yeah. Yeah, I don't know, maybe you can do this step. Maybe sigma 0 is enough here. But in any case, generally I want to consider sigma 1 elementary at least. So. Okay, so yeah, so there's this natural way to extend a given embedding V delta to itself into the unique possible extension of V delta plus 1. And so that and this process, moreover, is all definable over v delta plus 1, right? We've got the parameter, if we've got j, which is sigma 1 elementary v delta 1 plus 1 into itself, we've got this parameter j restricted to v delta. So definably in v delta plus 1, we can do this canonical extension process and figure out what j should do on a given set, right? All definably there.
Farmer, could I just ask? So these embeddings, I mean, if you have an embedding from v delta to v delta, it's got to be cofinal, right?
Yeah.
And so if it's sigma 0 and cofinal, then isn't it automatically sigma 1 preserving?
Well, when you say I mean, it can be sigma 0 but not cofinal. And
if it's from the structure to itself, doesn't it automatically?
I was going to mention this in a second, but
okay.
So yeah, I think it comes up in like the next. Let me see. I can stay now. So I'm just saying that you could have sigma 0 j from here to here, but not cofinal because you.
Sorry, I can't see what you're writing.
Oh, sorry, it's here. If we can have a sigma 0 embedding from v delta to v delta, which is not cofinal just because it's, I mean, suppose v delta models ZFC and you just take the ultra power by a measure and the ultra power is transitive, then, so it's an elementary embedding from the v delta into the ultra power. But then the ultra power is transitive subclass of v delta itself. So that's sigma 0 elementary. That's a sigma 0 elementary substructure. So in the end, that embedding is also a sigma 0 elementary embedding from v delta into v delta. It's just sort of silly.
I see. Okay.
But not cofinal, right? It's not preserving. It's not mapping v alphas to v alphas is the thing.
I see.
Yeah. Okay. Okay, so so Suzuki's theorem blocked definable from parameters elementary embeddings from v into v, but that if we replace v with this v delta plus 1 here, then that fails, right? Because we can define it from this restriction, and it fails in a strong way because every embedding of this form is definable from parameters. In fact, it's definable in a uniform fashion from a certain parameter. Yeah. So we get sort of a very different picture compared to the one with Suzuki's at a ZF model. Okay, so just a bit of some standard tools here. If we have a j v delta to v delta sigma 1 elementary and delta a limit ordinal, then we define the iterates of j just by repeated application. So j, I just want to say j0 is j, j1 is j0 of is j of j, j2 is j1 of j1, and so on. So basically the same thing as if you had a measure and you were linearly iterating by forming ultra powers through the finite iterates. Obviously I can't write j of j literally itself because j is not in v delta, but j plus, we have just defined the canonical extension, is a map from v delta plus 1 to v delta plus 1 that shifts j to something, and so that's what we want. We're just taking j and moving the initial segments of j up with itself, and that gives us some other function up there. Okay, so if we do this, yeah, so then if we start with sigma 0 elementary embedding v delta into v delta, that was a limit, then, yeah, so this is sort of relates to your question, j is sigma 1 elementary if and only if j preserves the rank segments, right? So sends rank segments of v to rank segments of v for all alpha less than the height. That's takes a little calculation to do it, but that's a straightforward thing. And then it follows that if the j to begin with is sigma 1 elementary and we form the iterates, then all of the iterates are also sigma 1 elementary. So j sigma 1 elementary, so it preserves rank segments. So when you apply j to itself, that's going to be another function that preserves rank segments, and it's like sigma 0 elementary, and so you get this preservation. And then so all of them are sigma 1 elementary. And in fact, you can prove the same thing for sigma k elementary, that if j is sigma k, then so is jn, but that's not obvious. It requires more argument, and it'll come up, the ideas for that will come up a bit later. It's easy to see if j is fully elementary, then all of the iterates are fully elementary, because you can say for each n, you can sort of talk about sigma n elementarity and get that preserved, and then the iterates are fully. The critical point of Jn is the same thing as what I wrote earlier as kappa nj, these kappa nj's. These kappa nj's, I mean, however, that's not trivially true, because the kappa nj's were defined by repeated application of j itself, whereas here we're defining the critical point we're defining the jn's by, the critical point of jn plus 1 is jn of its own critical point kind of thing. So you're using a different function, but it's easy enough to see that these are actually the same.
And can I ask, and so like j sub 2 is also j plus plus of j?
Yes, and I'll state that it's j plus of j1. So I mean, by definition, the definition I gave was j2 is j1 of j1, but it's the same as j of j1, which I'll mention later. Okay, I'll need that later. Okay, so I'm just going to look at first, just for a bit of motivation, look at a simple example of some of the questions. So if we have a sigma 1 elementary j v delta is v delta, which is like an I3 embedding under ZFC, so then this critical sequence is just delta itself, right? The kappa omega being the super of the critical sequence is just delta. So that's the same as the limit of these critical points of the iterates. Then, so we have, for example, the question about uniqueness, can J be the unique sigma 1 elementary V delta to itself, which extends some restriction, J restricted to V alpha, for some proper segment? Well, it's easy to see it can't be, because there's the picture. So we have the iterates here, J0, 1, 2, and so forth. And now we've got some V alpha, and we're looking at J restricted to V alpha. So it's asking, does that isolate J in terms of sigma 1 elementary embeddings? Well, no, because just look at J of alpha here, and there'll be some Jn that goes up higher than here. So look at this kappa n. Jn here has critical point above, equal to kappa n above this J alpha. But then if I just look at the composition here, so K is Jn composed with J, K is Jn composed with J, then this is a new embedding that it's not, as Jn had critical point up here, so it's not changing what J did down below V alpha. So these two embeddings are going to agree, K and J are going to agree below V alpha, but they're distinct embeddings. I mean, this kappa n was the image of kappa n minus 1 under J, but when I compose now, so J moves it up to kappa n, but when I compose, the compose map sends it higher. So these are different embeddings. So you can't, in this case, it's easy to see you can't isolate with some initial segment. And then similarly, the question, can J be definable from parameters over V delta? And if J is fully elementary here, then you can do a similar kind of argument. If you had some parameter P here, and you can define J from that P, you can then find, it's like in this picture, if J2 has critical point above where P is, then you can look at the composition J2 with J, and you sort of shift the definition of J, but you fix the parameter. So when you fix the parameter, it sort of shouldn't change what J is going to be, but really it does, because it messes up what's going on up there. So that sort of argument works there. That doesn't seem to work for when J is only sigma 1 elementary, because you've got the definition of J, and why should if J is sort of arbitrary complexity, then this J might, when you apply the J2, it might not be preserving what that is. But anyway, we'll deal with that in a moment. So, but this just indicates that there are some easy answers here in this case. Suppose though now we instead
so
have,
it's kind of like saying that that J can't be as as preserving as its own definition or something like that.
Yeah, right. That looks like that.
Right. Kind of.
Yeah, right. If J2 was sort of more elementary than the definition, then you would shift something in the, you would get some X that's down here and a Y here or something, and move it up and get a new output for it, which would be telling you if J2 is that elementary, then it's going to preserve the thing. Yeah. Okay, so that's for an I3 kind of embedding, but suppose we're beyond there and we have J V delta plus omega to itself. So now here the critical sequence has to terminate strictly below the height of this v delta plus omega, less than or equal to this delta. So, you know, you can, these methods we just used, the parameters, you can't find an iterate that has a critical point up above there. In fact, obviously any elementary embedding from v delta plus omega into itself has critical point less than delta in this case. It can't be up here. So these methods won't work for this sort of embedding. So we need some other stuff there. In the end, we'll get some answers for this as well though. Okay, so the first theorem is this one. So if we have ZF, so in general, I'm just assuming ZF throughout. That's the background. So if J is V delta to V delta is sigma 1 elementary, non-trivial, then, so let's look at, so delta here is a whatever ordinal. So if it's a limit ordinal, then J is not definable from parameters over V delta. So that just works in general. If it's a successor and J is fully elementary, then J is not definable over V delta from any parameter in V alpha. So, you know, we already saw that if delta is alpha plus 1 and alpha is a limit ordinal, then you can use this canonical extension thing to define J from its restriction to V alpha. So that parameter is up, that's a subset of V alpha. So this is saying that rank is optimal. You can't do anything with a P of rank less than down in V alpha. There's in the proof, the proof of this uses a variant of Suzuki's theorem. I mean, of the, let's see, the proof of this limit, what am I going to say? Yeah, not for the fully elementary case. The proof of the fully elementary case, the one uses the a variant of Suzuki's theorem, and Richard Matthews proved independently a related fact. So I don't know if you've seen this thing, you'll see that's a similar thing that comes up. I'm going to mention this again a bit later because it's also related to a thing that comes up later on a bit more closely. So I'll mention that in a bit more detail later. Okay, so yeah, as I mentioned before, sigma 0 here is not enough for this theorem because, right, because we might have V delta, and V delta just models EFC, let's say, and then we might have a ultra filter mu. Just take the ultra power of V delta by mu. So this gives us J V delta into M. M is the ultra power, but M is transitive, and so you know M is sigma 0 elementary in V delta itself in this case, and so therefore we can just look at J if we want as a sigma 0 elementary map from V delta to V delta, but you know this one is definable from the parameter mu here. So yeah, so sigma 0 is not enough. Okay, so I'm going to go to look at the proof, first assuming that J is fully elementary here. Oh, sorry, that's not there. I could mention that. Yeah. Okay, I guess I'll use flat pairing in the thing. So let's state this before I look at the proof. So yeah, so we use flat pairing and so forth. So if P and Q are elements of V alpha, then the pair of P and Q is also an element of V alpha. Okay, so when alpha is an infinite ordinal, right? So it's not the Kuratowski as it pairs, but I don't know if that's right. But anyway, we use flat pairing, so we preserve this sort of rank. And similarly, omega sequences, if Pn is a subset of V alpha for all integers, then the sequence of them is again a subset of V alpha. So you don't increase in rank there. Yeah, so in particular then, also if you've got an embedding V alpha to V alpha, so that's a set of ordered pairs, X and Y in V alpha, that's that set there, then this is in V alpha plus 1, right? It's a subset, it's a set of pairs, so they're like this, so they're all in V alpha. The set of them is subset of V alpha, so it's in here. So you get these things for flat pairing, and the flat pairing, defining the flat pairing, and going from P and Q to the pair and going backwards from the pair to P and Q themselves is a simply definable translation. Okay, so I want to talk about the proof of this theorem in the case that J is fully elementary. Okay, so we got I'm going to work with this on the left. So we've got, I might make this larger for the moment so that did that go larger? Or is it still?
Yes.
It did. Okay, cool. Okay, so we've got this V delta, and we're looking at some V alpha, and P is a parameter in V alpha, and we're going to assume that J from V delta is fully elementary. So that's J goes V delta to V delta is elementary, and J is definable. So J is like the set of pairs X, Y in V delta, such that V delta satisfies the phi holds of P, X, Y. Okay, now I want to generalize that to be able to define the same kind of thing from any parameters. Let's call this one JP, and then JQ is likewise, but we replace the P with Q there. It's the same definition. So for Q, any element of V delta, you have that. Okay, and now let's look at the AN being the, okay, so this JQ, right, in general might not be a function, it's just some set of ordered pairs. So it might not be a function, V delta, it might be partially elementary, it might be fully elementary. So let's look at AN being the set of Qs in V delta, such that JQ is sigma n elementary from V delta to V delta. So it is a function and it is sigma n elementary. So A omega, so this n here is less than or equal to omega. So obviously A omega is just the intersection of the ANs. Okay, and our assumption is we've got a P here in V alpha, which is in, P is in, it gives us a fully elementary map, and it's in V alpha. So this A bar n, let's just restrict the ANs down to V alpha. So this is V alpha intersect AN. Okay, so now I've got, you know, this AN here, some subset, A bar n, some subset of V alpha. Let's take the sequence of these things. So since we use this flat pairing, the whole sequence is also an element of V delta. All right, so even if delta is alpha plus 1, it might be right at the top, but this sequence is coded appropriately, is also an element of V delta. Okay. Now, so we want to use the trick that is used in Suzuki's theorem, which is basically that you take the least critical point of any embedding, which is any elementary embedding, which is defined from this formula, and move that least critical point up, and then say, well, you know, I mean, the fact that this kappa 0 is the least critical point that's defined in this way gives an elementary embedding. You want that to be first order somehow, and then you apply the embedding, and it gets shifted up. Now it's higher, and now this higher version is now meant to be the least critical point of such an embedding, and you get a contradiction. Okay, you have to think about somewhat how to get that to work, but yeah. Okay, so we're going to do that sort of thing here, but yeah. So we will take kappa 0 now being the minimum critical point of such an embedding. So we look at all the parameters that are in this V alpha, that they're in the A bar n's, A bar omega. So yeah, so A bar omega is then the intersection, right, of these. So we know that P is actually in here, right? So this is not empty. So let's take the minimal critical point of all of them. So I mean, minimum of all the critical points of JQ, such that Q is in, you know, in this A bar omega. So that's just saying that, i.e., JQ V delta to V delta is elementary, and Q is in V alpha. So those two things. Okay, so that's the minimal critical point. Take a witness Q0 to that. So Q0 is in this set A bar omega, and it hits the minimal critical point. So Q0, yeah. So and set J0 equal to this embedding. So we get that the critical point of JQ0 is equal to kappa 0, the minimal, and J. Sorry, I'm calling that J0 now. J0. There. J0 is that. So J0 is fully elementary. Obviously, I don't mean J with the parameter 0, but it's just notation. Okay, so that's what we have in our picture here. The kappa 0 is the critical point, and getting moved up by this J0, and Q0 is the parameter defining it. Okay, now let's look at, yeah, so now we want to get this contradiction. So we've got the image of kappa 0, and we sort of want to say that that one should now be the minimal one or something like that. I won't argue exactly like that, but basically. So J0 is fully elementary. So when I apply it to A bar n, here I get the I just get AN intersect this rank segment, right? I mean, you know, AN was defined. This AN is just the set of parameters here, such that this resulting JQ is sigma n elementary. So that's just definable, outright definable without parameters, this AN. So when I applied a fully elementary map to it, it just gets preserved. So J0 of A bar n is just then its intersection with this rank segment. So I get this. And so in particular, Q0 is in there, right? Because I mean, obviously alpha gets shifted up to J0 alpha, so we're just getting more, but the AN part is still the same. So Q0 is in there. J0 of the entire sequence is just the, you know, the sequence of the A bar n's. So these guys, since omega is obviously fixed. And J0 then of A bar omega. So A bar omega is just the intersection of the A bar n's. So this is the J0 of the intersection A bar n less than omega. And this is just the intersection n less than omega of the J0 A bar n's. Okay, and I know that Q0 is in each of these, and so Q0 is in here as well. So Q0 is there. Right, so, but now this Q0 is something that yields an elementary embedding with critical point kappa 0. And now that gets seen here. So, you know, we've shifted the set A bar n, draw that like this. This is, or A bar omega is this set here. I've shifted it up and it's become some set here, but it's still got, J0 A bar omega, but it's still got Q0 in it. And you know, the fact that Q0 is in there, and yeah, this can be seen. So V delta models, then that there exists this Q, which is going to be Q0, the witness, such that this is in J0 A bar omega, and the critical point of JQ is less than J0 of kappa 0. J0, this is just a parameter. You know, these two things are parameters here, right? This one and this one. Okay, so V delta sees that there is this Q0 in the set with a critical point here less than J0 kappa 0. So, but that's just elementary statement, right? I mean, here, these are just parameters in the range of J0, so I can pull it back. So that gives me V delta satisfies there exists Q in A bar omega, and the critical point of JQ is less than kappa 0. But A bar omega is exactly the parameters that give me in V alpha that give me fully elementary maps, and I was supposed to choose kappa 0 as the minimal critical point of one of them. So now this is contradiction. So it's contradiction to the kappa 0 choice. Okay. Okay. So that gives us that. Yeah. So, okay, as a corollary to this, there's a curious thing that happens. If you have, yeah, so we saw that if J is sigma 1 elementary V lambda plus 1 into itself and lambda a limit, then J is its own is the canonical extension of its own restriction, right? So there's a way to recover that sort of J from its restriction to the V lambda. Well, okay, yeah, well, then we can ask, is that going to happen at V lambda plus 2 if we go up a level? So let's look at J in EV lambda plus 2, where lambda is a limit. Then it follows that from the theorem and this here, that J is not definable over V lambda plus 2 from this restriction of J to V lambda plus 1. Because if it was definable, then also that one E was, yeah, fully elementary. Yeah, so notice, okay, I had E, just talking about a sigma 1 elementary map. Here I'm talking about this script E means fully elementary, right? At the moment, I'm assuming J is fully elementary here. Okay, so J is fully elementary V lambda plus 2 into itself. Then J is not definable over V lambda plus 2 from this restriction. Because if it was, then J is actually definable from the smaller parameter, J restricted V lambda, because we know that we can recover J restricted V lambda plus 1 just as the canonical extension. So this is enough, but we just saw that in this case, you know, that this thing here is in V lambda plus 1. So think about the theorem in the case that alpha is lambda plus 1 and delta is lambda plus 2. We've now defined the full map from this parameter here, which is too small according to the theorem. So, you know, something changes between lambda plus 1 and lambda plus 2. Of course, that doesn't rule out other parameters in V lambda plus 2 of maximal rank. So we have to still consider that. And it also doesn't tell us much about lambda plus 3, you know, whether this could be definable from this restriction or from any parameter that's at this point is not clear. Okay, so I'll come back to these questions later. Yeah, so as I said here, so I'm going to now consider the partial elementarity case, but in that case, we're just looking at a limit ordinal, not successor. Okay, so that's what I'm going to discuss here. So now we're going to look at the version of the theorem where we've got a limit ordinal and just a sigma 1 elementary map, and I want to see that that's not definable from parameters. So the key to this is the following lemma, that if we have that situation, then one of the iterates is actually fully elementary. So we can just replace J with the nth iterate. The iteration process is definable. So if J in the first place was definable from parameters, then each of the iterates are, and then this Jn, which is fully elementary, will contradict the theorem. Okay, to contradict the first part of the theorem. Okay, and so the proof sketch is as follows. So if V delta now is this limit rank segment, yeah? So if this models ZF, our J is sigma 1 elementary. If V delta models ZF, then it's automatically fully elementary. So this is stated in Geifman's paper down what I mentioned here, and he seems to say there that that's well known at that time. So I'm not sure who that fact is due to, but yeah, it's a straight. So if so you've got a sigma 1 elementary from V delta into itself, and it doesn't have to be V delta into itself, but that's our case here. Because V delta models the F, you look at the, for each n, there's a club of alphas where the alpha's sigma n elementary in V delta, and sort of by analyzing that club and what J is doing, you can go by induction and prove that it's sigma n elementary for each n. Okay, so let's assume then instead that V delta fails ZF, and so we've got some failure of collection. Right, we've got a rank segment, so obviously it models separation and everything else, so it's a collection that fails. So we take some x in V delta and some function then that's from x into the ordinals, into delta, which is cofinal and definable from parameters. So that's exactly what it means to have a failure of collection, or equivalent. Okay, and then we consider this induced pre-well order of this set X, right? So we've got this function on X going into, in this picture here, we've got this function on this set X going into cofinal in delta. And so we can get the pre-well order where we're just cutting X up into the slices according to the ordinal that they get mapped to. And so that gives us a pre-well order. This X star below Y if Fx below Fy. Okay, and so the fact that we use is this theorem of Geifman from 74, that in this situation, J is fully elementary if and only if the pointwise image of J on the set X is cofinal in J of X, actual image of X, with respect to the shifted pre-well order. So, so our picture is we have the X here and the ranks in there. So they're getting shifted to some ranks inside J of X. And, the soup of these things might be bounded or they might be unbounded and inside J of X. And so that's the distinction. And that determines whether J is fully elementary here. If you've seen my write-up of this in a paper, then I didn't cite Geifman here because I only realized that Geifman proved this fact a couple of days ago, but it's there. It's hard to get hold of this paper online. I couldn't find this paper, but one can get it from a library. So it's kind of old-fashioned. Okay, so Geifman's result is actually more general than just, he doesn't talk about V delta into V delta. He's talking more generally as M into N, but proves it in that context, but it doesn't, it's the proof is the same kind of thing. Okay, so we want to use this. So we want to replace our J with an iterate where this is going to happen. And so to get to there, so I guess, one case of that, in one case of that, delta is singular definably over V delta. And so that would be delta here. And so we'd have gamma, the cofinality, and then there's just some definable function from gamma into delta. So, clearly if J of gamma is gamma, if we have J of gamma equal to gamma here, then J applied to gamma is also cofinal in J of gamma, and then that would give us what we want. So that's the basic point, is that some iterate is going to fix that any given ordinal. And then, there's another case where it's not, where delta is regular but not inaccessible, but the same kind of argument works. Okay, so that's what we want to do. We want to take a given ordinal alpha less than delta and see that some iterate of J is going to fix that ordinal. And this is just like basically the standard proof of linear iterability for measurable. So first of all, yeah, as was mentioned earlier, that I defined Jn plus 1 as Jn of Jn, but it's the same thing as J of Jn. And that's easy enough to see. So for n equals 0, that's just by definition. J of J is J1. For n equals 1, it's this. So if n equals 1, we want to see that J of J1 is J2. So J of J1, well, J1 by definition is just J of J, but we can distribute. So that gives J of J of J of J. But that's the same thing as J of 1 of J1. So that's J2. And then it's similar later. Okay, so J of Jn is just Jn plus 1. Okay, and then if Jn fixes some object, then all of the later iterates also fix the same object, which is also clear. Like, the fact that Jn of x equals x is just part of that function. When we apply Jn to that statement here, we end up with Jn plus 1. Apply Jn to it, Jn becomes Jn plus 1, x becomes Jnx, x becomes Jnx, but x was fixed, so these guys are actually equal to x, so that tells us Jn plus 1 of x is x. Okay, so Jn mapped this thing to this thing, but it didn't move on there, so the Jn plus 1 does the same thing. Okay, so that's like that. So in particular for ordinals, we want to consider once one of them fixes the ordinal, then all the later ones fix it. Okay, so then the fact we want is that for every alpha less than delta, there is some stage n where some iterate n where Jn alpha is alpha. So that's in this picture here on the left. Okay, so suppose that's false, and we take the least counterexample, alpha, and so then J alpha is strictly bigger than alpha. So now let's just look at the ordinals below alpha. We know that each of them is eventually fixed. So just look at the set of ordinals beta less than alpha, such that Jn beta equals beta. Jn fixes it. So that's some subset of alpha here. So we have this An here. On the left here is a subset of alpha. But we know that alpha here is just the union of the Ans by our minimality of alpha. Yeah, and that's a statement, delta 0 statement there, satisfied in V delta. So we can apply J to that statement, and J of the sequence of AN, the sequence of ANs is in there. J of the sequence is just the sequence of the J's. So by the elementarity, we get that J of alpha now is the union of the J of ANs. Right, so we've pushed that, but J of alpha was bigger by choice. So there's J of alpha, the entire thing is getting contained in the union, or it equals the union of the JANs. But alpha's there. So then alpha's in this, alpha's less than J alpha, alpha's in this union, so it gets into JAN for something there. But what's this JAN? This is just the fixed points of JN plus 1. AN was the fixed points of below alpha of JN. But we know J moves Jn by that claim. J moves Jn to Jn plus 1. And so everything in here in Jn is fixed by Jn plus 1. And therefore, we've got a contradiction. Alpha is actually fixed by Jn plus 1. Okay. So that gave us that it got fixed. And so that gives us what we wanted. If delta was singular and gamma is the cofinality, sort of, it actually follows in this case. Our assumption was that V delta is definably, there's some function cofinal from a set cofinal in delta. If delta is also singular, then it actually follows that it's definably singular with its with its cofinality, because you've got all the sets down there below it there anyway. Okay, so if we have this, then we've gotten some iterate that fixes gamma, and then J and pointwise on this is cofinal in that, and so then we can apply Geifmann's theorem with this, and we get that Jn is fully elementary. And it's this, so the other case is delta is regular, but there's some set. So X is V alpha or something, and from V alpha we can map cofinally into delta. So by regular here, I mean with respect to ordinals. But there could be some V alpha that maps cofinally in delta. But then you can still do a similar thing where, if you, instead of looking at these ordinals, you're thinking about sort of arbitrary pre-well orders of a given V alpha, and those pre-well orders kind of replace the ordinals in the argument we just gave, but you do a similar kind of calculation. And so that still gives that we can get an iterate where this pointwise image is cofinal, and then we get the elementarity, the full elementarity at that iterate. But the original J was definable from parameters, was our assumption. So is every Jn, and then we get a contradiction to the theorem, to the first part of the theorem. Okay, let's see, what's the time? Yeah, no, I've pretty leave that. Okay, I was thinking of mentioning something about the Geifmann's proof, because it's a central thing here, but I think I'll skip that for now. Okay, so just a remark, the iterating step is necessary. So there are cases where you have a partially elementary map and you need to iterate some distance to get it elementary, and you can sort of need to go arbitrarily far. So if you get an elementary V lambda plus to V lambda, so this result is with Andreas Leitz. If you've got a elementary embedding from V lambda plus into itself, I haven't really thought about whether this is, that might be overkill. Maybe you can do this thing with less than V lambda plus to itself. Okay, if you've got that, then for every integer, you can get a restriction of this J down to some lower ordinal, such that this guy is sigma 1 elementary, but the first n iterates are not sigma 2 elementary, and then the n plus first is elementary. And then similarly, okay, so that's with sigma 1, but you can do a similar thing with sigma m elementary for the first n iterates, and then yeah, instead of sigma 1 here, that at least if you have a Reinhardt cardinal, then you can do that. Yeah, as I say, I haven't really tried to see whether these assumptions are optimal to get that. Okay. So, and also the theorem, the limit case theorem can be executed a little more carefully in, so, you know, I've been working with a rank segment of V, and the ZF is the background theory. But instead you can replace that with the natural theory of limit rank segments, which is Z plus. So Z plus is a mellow plus this statement that for every set there is a V alpha. For every X, there is a V alpha such that which exists, you know, and X gets into there. So, you know, you can construct them, you know, so we get this. So this is sort of the natural theory for all limit rank segments, and that theory is enough to run this theorem, to run the proof that if we work in this theory and J v to v is definable from parameters, then it's not a sigma 1 elementary map, and it's the same proof, just done a, you know, a little bit more carefully. Okay. Okay, so that was, I guess this is switching topic a bit. So is there any questions at this point? It's okay. Okay, so I'm going to now consider constructability instead of definability. Yeah, so this is, well, let me just read the theorem first. So J, if J v delta into itself is sigma 1 elementary and delta has uncountable cofinality, so in particular it's a limit here, then J is not constructible from v delta. So yeah, the delta inaccessible case was done earlier independently by Goldberg, and then the general case I did. The two proofs are different. Okay, so yeah, so here I'll just give a sketch of the proof. So the basic point is, you know, we have this J from V delta to V delta, and we've constructed it, and we want to try to extend J to a fully elementary embedding from, to an embedding from the full L of V delta into itself, which is definable from parameters, and then that will contradict Suzuki's theorem. Okay, and so the method for doing that is we take an ultra power by the extender derived from J. So if I'll say what if you haven't dealt with extenders before, it doesn't really matter, but it's similar to taking ultra power by a measure. So anyway, I'll describe it a little bit. However, there's one step first, is that we do that iterating kind of thing to get, so if delta is not inaccessible, and there's some function from a set in V delta cofinal into delta, we can do that iterating step to get to a point where the iterate maps the set X cofinal into J of X in the same way as what we just did in the previous lemma. You know, I mean, the plan here is we want to extend J to be a fully, to be an elementary map from L of V delta into L of V delta that fixes delta. So in order to do that, it would have to be elementary from V delta into itself in the first place. Otherwise, there's no possibility. So if we started with an arbitrary J, then we should replace it with this iterate where it's at least fully elementary. And you need to do that even if J was fully elementary in the first place. You also need to do that for other reasons that come up, but I won't really explain. Okay, so we make this replacement first. Okay, and then, so we look at the extender derived from J, right? So this is just this system of measures of this form. So I can just draw a picture of that. So we have now V delta, and J is going into V delta, and that's not visible there. Yeah, and so given any A over here, we can look at the sets X here such that J of X, such that A, sorry, gets into there. Okay, and so that gives us as usual, gives us an ultra filter over V delta, or over some V alpha. We can take V alpha here and subsets of V alpha. Okay, so we call that EA, the measure derived from with seed A here. You know, there's different ways you can set this up, and I'll just say appropriate finite sets A in here. You know, you have to decide what one has to decide what appropriate means and set this up carefully, a little bit carefully, but this is the basic point. Okay, so then we can define the ultra power of V here. We're working in L of V delta as our assumption. We've got the J there. So we can define the ultra power of V by this extender. And so, you know, you define the ultra power of V by one of the component measures, one of these EAs in the usual way. And then the full ultra power of V by the extender is a natural direct limit of all of those ultra powers. Okay, and then, right, so what we want then is that ultra power is well-founded and the whole ultra power is elementary. And you get those things. So we can prove, in this case, a version of Walsh's theorem. But, you know, of course, the usual proof of Walsh's theorem requires AC, right? And we don't have AC here in general. But we've got L of V delta, and so sort of modulo V delta, we've got choice above there, because we're just constructing. So in this situation, that sort of allows you to do Walsh's theorem. However, it's important here that we've done this step at the start, you know, taking this, increasing the elementarity sort of the embedding to start with. You know, we want to extend it to this fully elementary embedding. So, you know, and Walsh's theorem is sort of guaranteeing that that happens. So it sort of makes sense that you need to do this step to get Walsh's theorem. It's not, you know, that you have to be a little bit, I say a version of here, so it depends exactly how you state. So you get Walsh's theorem for the extender, but as I recall, the proof doesn't seem to give you Walsh's theorem measure by measure. So if you just did ultra power of EA by itself, maybe it factors in, I don't know. Anyway, yeah, I think there seemed to be some difficulty if you wanted to do it measure by measure. Anyway, we can get it for the full extender, and so that gives an elementary embedding, and the ultra power is well-founded, and the well-foundedness is where we really use the uncountable cofinality of delta. So a failure of well-foundedness, you can sort of reflect into some smaller piece of the embedding and get a contradiction. Okay, so we get this, right? So we've gotten this U, which is well-founded, and it's this elementary embedding. But, you know, because we've got an extender here that like covers sort of everything in V delta, then you get that V delta is a subset of this ultra power, but this is working in L of V delta. So in fact, U is the full L of V delta is V. So that gave us an embedding V into U, V into V, but it was definable from this parameter E, and so that contradicts Suzuki's theorem. So we kind of had this sort of J here. Okay. So that's the uncountable cofinality case. So we can ask what happens if delta has countable cofinality in L of V delta instead, in V or in L of V delta is the case that matters. So suppose we have this, and J is elementary from V delta to V delta, but J now is just in V. We're not assuming it's in L of V delta. So can we find such an embedding in L of V delta? I mean, there's a natural method to try to do that, because, you know, you have V delta, limit ordinal delta, you've got all of the initial segments of the J that's in V. So you can try to put together a sequence of initial segments that union up to form a fully elementary embedding. And there's a natural tree that's natural tree of attempts that attempts to build such a thing by initial segments. You know, we have V delta. We can look at alphas and betas here that map some V alpha into K, maps V alpha into V beta, and, you know, so that's sort of a node in the tree, such an embedding, and a deeper node extends that embedding to higher, to more domain kind of thing. You know, you've got the cofinality is omega, so you can make sure that as you go through along a branch of the tree, you're getting all of the domain V delta into the embedding when you take the union. So you can get this tree, and any cofinal branch through it would correspond to an elementary embedding. And so we got that way, you know, you can form that tree in L of V delta. You know, however, there's sort of difficulties with getting branches here in L of V delta if you don't have choice or you don't have DC or something in L of V delta. So it's not sort of immediate that you get something in here in general. However, it is consistent to get enough choice to do it. So relative to I1, you can do this, and you can get such an embedding in L kappa plus 1 of V delta, where kappa is the least admissible beyond V delta, at least such that L kappa V delta is admissible. So this corresponds to, you've got this tree, you've got the Cantor-Bendix analysis of the tree, and that sort of stuff terminates by the admissible, and so these things are naturally related together. Okay, so it is consistent relative to I1 to arrange this. The only way that I know to get that, though, is that the V delta models ZFC, and in fact models V equals HOD, and so L of V delta in that case models axiom of choice, and you only get an I3 embedding V delta into itself. I don't know any examples where you without L of V delta modeling choice and anything beyond an I3 embedding in L of V delta. Anyway, you can get it here, and then, but actually it turns out that that's optimal. So if you've got any elementary embedding V delta to itself, where delta is a limit and kappa is least such that L kappa V delta is admissible, then J is not in there. So L kappa plus 1 is the least level you could construct it at. And so the proof of this theorem is a variant of the one for L of V delta, where delta had uncountable cofinality. So the idea is here, so suppose you've got such a J in L alpha V delta, and alpha is less than this admissible. So then again, we look at forming an ultra power of say L alpha V delta by the extended derived from J. I guess we first iterate that J to make, okay. Okay, but the key new issue now is that the ultra power might be ill-founded because you don't have the uncountable cofinality. Okay, we can assume here, okay. Okay, so it might be ill-founded, right? So however, V delta, when you take the ultra power by this extender, you certainly get everything in V delta, that's the same, but then sort of delta is the least point that might be ill-founded. However, you can arrange that delta is at least in the well-founded part by doing that sort of iterating in the first place, so you can make sure the the ultra power embedding is continuous at delta, so it looks like this V delta to V delta. You can arrange that the delta maps to delta when you take the ultra power map of L alpha V delta into U, the ultra power, so you can get delta fixed. But then it might be ill-founded up sort of above here somewhere. Okay, so this is ill-founded part. Okay, so so we can get the delta fixed. Okay, so the key new issue then is that we might have U ill-founded, but sort of higher than there. But there's a convenient fact here that says that in this case, actually L kappa V delta has to be contained in its well-founded part. So that's this fact here. If you've got any ill-founded model with say V delta in that model, and that model satisfies that I am L of V delta, it's ill-founded, then the well-founded part has to contain everything up to the first admissible. So that's a standard calculation, not too hard to see. So that's what have to happen here with our U. And so, now we've got a problem because we have V delta, we had V delta and this alpha and kappa, the admissible. We took the ultra power, but everything needed to form the ultra power was in L alpha, L kappa V delta is just like this piece here, L alpha V delta and the E, which is in here. So we form this ultra power U as some set in working inside L kappa V delta. This U itself is not transitive yet, and it takes some constructing to compute the transitive collapse, but that doesn't really matter because below the kappa, everything's really coded by subsets of V delta, and all the power set of V delta intersect the U. This part can be immediately computed from this compute from from the U at the representation level. So when you compute the ultra power in terms of like equivalence classes of functions and so forth, where you can compute from that information, you can directly compute this collection of this power set. But all of that, that tells us now the power set of this full L kappa V delta is, in L alpha plus 1 V delta or something, and that's a contradiction. So we get a contradiction there, and then you can do it. So you get it well-founded, but then with a bit more work, like with these sorts of arguments, then you also rule out the well-founded case. Okay. Okay, so it's this optimal thing. The J prime you can get an L kappa plus 1 V delta, at least in a special case, but it can't get, in general, it can't get in any earlier than that. Okay, and then these ideas lead to a sort of strong non-uniqueness nature of these embeddings, which is as follows. So, so we have this sort of tree of attempts to build an embedding. In general, you don't have DC. If you don't have DC, that tree might not sort of really give you. You might not have cofinal branches through that tree. But you can always go to a collapse extension in VG and then find branches through that tree in the collapse extension. So that's what we'll do here. So if G is V generic and J is an elementary V delta of the ground model into itself, with J appearing in VG, we'll say J is V amenable as long as all of the restrictions, J restricted to each V alpha less than delta, if they're all in V in the first place, right? So this J is just a virtual embedding V delta into V delta, but all of the restrictions are in V. Okay, and so if we have that situation, delta's the limit and J's elementary V delta into itself, then we can go to a forcing extension. I think G just being the collapse of V delta, I think was enough. And in that forcing extension, for every alpha less than delta, we get a V amenable elementary embedding V delta to itself, such that it agrees with the given J to begin with. We had this J at the outset. So this new J prime will agree with J through this given alpha. So J prime through V alpha is the same as J through V alpha, but they're different. So J prime's not J. So, you have this J V delta into V delta, like this. Whatever V alpha you choose here, and J restricted to there, generically, I can produce an embedding that agreed with this through this piece, but then diverges somewhere above there. And G can as long as we have DC and coef delta is omega, then we can take G empty here. So we can actually find these embeddings in V if we have these conditions. And the proof is, so the main ideas in the proof are similar to what happened in the proof that you can't construct an embedding too quickly in L kappa V delta. So you're looking at the kind of tree of attempts to build one of these embeddings, and you have to prove that tree is sort of very thick, and that leads to the relates to this, what happens in here. So basically you get something like this perfectly many embeddings. I mean, in the DC coef omega case, then you get this tree which is perfect and giving all these embeddings. Okay. In the case where you don't have DC or coef delta is not omega, you still got this tree. It's just that maybe you can't find branches through it. Okay. What's the time now? It's here. Okay. Whoops. Okay, and then so now I'm going to move to the successor case. So I mentioned the question earlier about what happens in the we had embeddings V lambda plus 1 into itself definable from the restriction to V lambda through the canonical extension, but that failed at V lambda plus 2. So now we're going to sort of look at that what's going on in the successor stage case in more detail. So Gabe analyzed in 2017 the elementary embeddings of this form V delta plus 2 into itself for limit delta in terms of ultra powers, and I'll mention this a little bit in a moment. And then building on this analysis and on some of the stuff I've mentioned so far, with the following theorem. So this theorem's independently earlier due to Goldberg as well. But yeah, so but both of us using this analysis, right? Okay, so if we have ZF, alpha is an ordinal and J, V alpha is elementary, then we get that J is actually definable from parameters of V alpha if and only if alpha is odd. So, so odd here is in the obvious sense. If lambda is a limit ordinal, then that's even, and then lambda plus 1 is odd, lambda plus 2 is even, and it oscillates. Okay, and okay, just in connection with this, if so this is saying that for such okay, so so this says that there's sort of a strong structural difference between the even and odd levels in the cumulative hierarchy. The elementary embeddings are definable from parameters or not is sort of a something quite different between them. And yeah, so but you might ask then, for which ordinals does that hold? Do we have elementary embeddings from V alpha to itself? So obviously it's a very strong large cardinal principle to have it even at delta plus 2. But okay, but just a note here, if we have a Reinhardt embedding from V into V, then after some point onward, all V alpha admit such elementary embeddings. That's just because you use the iterating thing. If you have J V to V, then you look at the iterates of V, the iterates of this J, then every ordinal is eventually fixed by one of the iterates, and then you get one of those restrictions gives you a V alpha to V alpha embedding. That's for everything above the lambda of the embedding that works. Okay, and so we get this periodicity for every ordinal, at least this lambda. Okay. Okay, the idea of the proof now. Okay, I don't know. Am I sort of out of time now, or is the?
You can still go on a little bit.
Okay. Okay, I'll try to do it quickly because I'm
fine.
getting toward the end. So
Okay.
the idea of the proof is as follows. So if you have a J that's V delta plus 2, elementary V delta plus 2 to itself, delta is a limit ordinal. Then we can define an ultra filter over the set of elementary embeddings from V delta into itself. And this is if you've looked at Wooden's I0 analysis, is the same ultra filter that uses there. So we just define an ultra filter with seed is a J restricted to V delta, right? So we've got this V delta plus 1, delta plus 2. And then now we've got J here restricted to V delta. And so this J restricted to V delta is in V delta plus 1. And so we're sort of looking at subsets X of V delta plus 1, moving them across to J of X, and just asking whether J restricted to V delta gets into there. Okay, so that's an ultra filter and over V lambda plus 1, V delta plus 1, you could say, or over EV delta. This is a subset of V delta plus 1. Okay, so we can define the ultra power of V delta plus 2 by this ultra filter. And the ultra power map V delta plus 2 into the ultra filter. Okay, and then a key thing is you can show that the ultra power is actually equal to V delta plus 2. So everything in V delta plus 2 gets represented in this ultra power, and the original embedding J is actually the ultra power map. So every elementary embedding is of this form. It's a key. The key idea in getting that these are equal, that everything in the V delta plus 2 gets into the ultra power, is that we have the canonical extension, and so from J restricted V delta, I mean that gets into the ultra power just because it's the seed, so it sort of automatically gets in. But from that we can compute J restricted V delta plus 1, and then from J restricted V delta plus 1 you can compute everything else basically. So this gives you the full V delta plus 2. Okay, and then from this fact here, the fact that the ultra power is all of VDL plus 2, you can show then that J is not definable from parameters, this original J. And so the argument here uses that the ultra power map is cofinal. And yeah, so this is what as mentioned earlier, Richard Matthews had this had an independent argument showing that in a certain context you couldn't get a cofinal elementary embedding, and because it ended up being definable, and so that's sort of related to what happens here. We do get a cofinal embedding here in this case, but what we rule out is that it is definable from parameters. So yeah. So the argument is similar to the one I gave earlier. If you had a parameter in V delta plus 2 from which you can define the embedding, so it looks like delta plus 1, delta plus 2. We move across. There's some P here in V delta plus 2 from which we can define the embedding. So basically, it suffices to get that P is in J of X for some set X back in V delta plus 2, but that's the cofinality. Once you've got that, then you can run the argument from before, and so look at the the subsets of X that give you parameters that give you sort of sigma n elementary maps and so forth, and you can run the kind of argument from before. But this is what we get because it's an ultra power. So the fact that V delta plus 2 is the exactly this happens when you have an ultra power. So yeah. Okay, so that gives us that, and then so we have V delta plus 2 is the ultra power by this ultra filter. So now we could look at an elementary embedding V delta plus 3 into itself. We can apply the previous stuff to the restriction to V delta plus 2. And we can also form the ultra power of V delta plus 3 by the same ultra filter. So it's still the ultra filter that we got from V delta plus 2 and the corresponding ultra power map. Okay, so then now we know that the ultra power V delta plus 2 part gives you full V delta plus 2. So this new ultra power here contains V delta plus 2, but then also has some more subsets. But in this case, we actually get that it's not V delta plus 3. The ultra power here is smaller than V delta plus 3, but the ultra power map is the same as the J prime. So this J prime here and the ultra power map is the same thing. They have the same graph, but it's just the codomain. The ultra power itself is smaller than V delta plus 3. So the embedding J prime in the end is just definable as this ultra power map, and that's all definable over V delta plus 3 from the ultra filter we're using, which is this mu J. And so that gives us the definability of the embedding V delta plus 3 to itself from some parameter. And it's in a canonical fashion again, right? We always use this, for V delta plus 3, you use the embedding restricted to V delta plus 2, derive the ultra filter and do the ultra power construction, and that gives you the thing. And so this replaces, this notion here gives you a notion of canonical extension going from delta plus 2 to delta plus 3, which allows you to continue the induction, up to delta plus 4. You can use this notion of canonical extension to replace what we had going from limit ordinal to limit ordinal plus 1. And so it then starts to oscillate back and forth. Okay. Okay, and then just one remark here. Although the embedding V lambda plus 2 to V delta plus 2 to delta plus 2 can't be definable from parameters, that sort of has the feeling that there should be sort of lots of them, or there might be lots of them given extending any given initial segment, but that needn't be the case. So it is consistent relative to ZF plus I0. It is consistent to have ZF plus K maps V lambda plus 2 is elementary, lambda at limit, and N models that K is the unique extension of K restricted to V lambda. I mean, equivalently, K is the unique extension of K restricted to V lambda plus 1, because you can make that step, which is an elementary from V lambda plus 2 to itself. So it can be the unique one. It's just that it's not definable over V lambda plus 2. So, in V lambda plus 2, we can't see the object itself. But if you go to V lambda plus 3, then you can see it, and it's the unique one there. So we can define this K over V lambda plus 3 from this sort of restriction, but you can't define it over V lambda plus 2. So, okay, so that's all I was going to say, and I thought I'd just give a list of questions that bug me. That are, so that's the following. So first of all, if so, the theorem on like delta plus 2 and so forth being not definable for parameters works for fully elementary embeddings, but it has problems for partial elementarities. And so as far as I know, I mean, I don't know the answer to this. I don't know whether Gabe has an answer to this now or not, but if delta is a limit, or if anyone does, if delta is a limit and J is V delta plus 2 into itself is sigma 1 elementary, can that be definable from parameters? You know, the method we had for limit ordinals was to first of all iterate until you get a fully elementary embedding, but that method depends heavily on the fact that, you know, at a limit V delta, there's this sort of natural hierarchy of the sets leading up to V delta. You know, all the rank segments give you this simple hierarchy. But in V delta plus 2, for example, there's no obvious hierarchy on the things in V delta plus 2. And, you know, in some cases there is. If you're in L of V delta plus 1, then there's a constructibility hierarchy above V delta plus 1 that gives you a natural hierarchy, and then you have a hierarchy. But in general, this is really unclear, but it's sort of a very natural thing to sort of expect there to be a hierarchy in at least in sort of canonical situations, but in general, it's unclear. Okay, secondly, can an elementary embedding from V to itself be definable from its restriction to ordinals? So as I said, the restriction to ordinals is not definable from parameters itself. So this contains non-trivial information, but, you know, my feeling is that a JV to V seems to be very far from ordinals. So it would surprise me if you could define it from its restriction to ordinals. But I don't see how to get anywhere with this, like to, you know, assuming that's defined from ordinals. The arguments that work from parameters just don't seem to apply here. So I don't know. And then you can ask the same question for V alpha to V alpha. The constructibility stuff, L of V delta, you can naturally replace L with hard of V delta. So you can assume V is hard of V delta instead of L of V delta, and that delta is inaccessible, let's say. I mean, maybe you don't have to assume it's inaccessible, but that might be easier. Then can there in that case be a J V delta to V delta, which is elementary? So, you know, the method that worked for L of V delta has I took an ultra power, L of V delta turns into itself, but, you know, if you take the ultra power, but in hard of V delta, then you just might end, it seems you might just end up with a smaller universe. The ultra power might be smaller. I mean, it contains V delta and it satisfies I'm hard of V delta, but that's just internally, and maybe it's smaller than the original universe now. Okay, and then a couple of questions that are less related, but curious. So can we force a Reinhardt cardinal with small forcing? If you've got a forcing that's below the critical point, and then in VG, then you've got VG, and you can, maybe there's a, you know, you can get a J, which is a Reinhardt embedding over VG. Does that mean that kappa is Reinhardt in V? I mean, you know, obviously that you have to find some way to formalize that question appropriately, some work to say how you're working with classes there, but, you know, there's natural ways to try to formalize it. There's some partial results in this paper, but they don't really get at the main question, and in general, it's unclear to me. And then finally, then maybe there's an easy answer to this. It seems very odd. Anyway, the circumstance in this last one here seems very odd, but let's say that J and K are mutually coherent. If J and K are both Reinhardt embeddings, and, you know, we've got ZF with respect to J and K, the pair, we've got ZF JK, so we can talk about J and K together. And yeah. Okay, so they're mutually coherent if they're Reinhardt embeddings and they fix each other. So J of K is K and K of J is J. Yeah, so is that consistent? What is the strength? So, you know, obviously this is weird because, you know, if you had that sort of situation with like ultra filters or something, it's like saying that the two ultra filters are in each other's ultra powers and they fix each other, which, you know, so you know, when I first wondered about this, I thought you should be able to rule it out quickly, but I didn't see how to. So, and I don't see how to relate it to, like, you know, use in an interesting way to other things like super Reinhardt and so forth. So, okay, so that's the end.
Thank you.
Thanks very much, Farmer.
Yeah,
Sure.
thanks.
Yep. Thanks for the opportunity.
It was a very inspiring talk. Great. Are there questions?
Okay.
I have a minor question. Which Suzuki is this?
I can't remember his first name now, so I don't think I wrote it at the start, did I? So he's, but the if I go to the beginning, you can see at least the.
Mm-hmm. There's a reference to a paper at the beginning. A Suzuki.
Yeah.
Okay, thank you. There used to be a Suzuki at the University of Essex. I guess it's not the same guy though. Not Essex, Sussex.
Hey, Farmer, I had a question. This is just like, I don't know at all, but this is just, can one of your main theorems be restated like this? Okay. If J from V delta to V delta is sigma 1 elementary, okay, and if in an inner model which is minimal, which is definably closed and contains V delta, then J is not an M, and M is that inner model. Is that
yeah, you're saying L of V delta is the.
or just like, yeah, or just in general a minimal model which is definably closed and contains V delta.
Well,
Just
what do you mean? What do you mean a minimal model?
I don't know. Never mind.
Yeah. I mean, it does generalize more in that kind of direction. Like, if you take L of V delta sharp or sort of canonical, instead of constructing, you can add sort of canonical information to L of V delta, and the same kind of thing works. You take an ultra power, as long as you got to have that when you take the ultra power, you get the same universe back at the end. And so that works, at least to some extent, like adding sharps to V delta and much more. But then there's the question at the end of whether it works if just V is hot of V delta. So in that case, and there the proof breaks. Like so it works for a while, and then it gets fuzzy, and then lost. So.
Okay. Yeah, I'm not exactly sure what I was asking, so thanks. I mean,
yeah.
Thank you.
But that's the kind of, But it depended on the cofinality as well, right? That when delta had countable cofinality in that model, then it was different. But yeah.
Okay.
Yeah.
Thank you.
Yeah.
I wonder about this idea of considering objects that are unique as in some way definable. If it would be worthwhile looking at something like there is this idea of forming instead of the constructible hierarchy, forming the internally algebraic universe or something like that, where going from one step to the next, you don't add only things that are definable, but things that are as predicates you can put on so in a unique way. So you know what I mean, Farmer? Is there a way to consider that maybe?
I mean, there's the standard kinds of inner models we can add there, which give you unique objects like sharps and so forth. I don't know if you mean that or
no. I just meant like you were considering questions like could this J be the unique elementary embedding that continues some restriction of itself, right? And like if you build, so if it is unique but not definable from it in the structure that you look at, then you could consider you know, the next level in the hierarchy that
Oh.
you're building to contain this
To contain that,
J,
yeah.
because it's unique, and you would add everything that is unique with respect
Yeah.
to something, you know. So
Yeah.
that would be a hierarchy that kind of grows more quickly than just adding the definable stuff, but you're adding all the unique stuff, you know.
Yeah.
So I wonder if you can maybe do something interesting with that in that context. I don't know. Just.
Yeah.
I make a comment about that, which is not a very good comment, partly because it's tangential and partly because I don't remember any details. But it seems to me, okay, you're making this distinction between definable and uniqueness as an extension of definability. And of course, in model theory, we have this nice Beth definability theorem that says that in general models, these are the same thing. Now, the vague point is that I think people have considered sort of generalizing not only first order logic, but abstract logics and so on in a direction of building in the Beth definability theorem. So given some logic, you enlarge it to a logic in which whatever was uniquely specifiable in the first logic becomes just by fiat definable in the larger one.
Yeah.
So I should say a lot more about this, but I don't know a lot more about it, so I'm going to shut up.
Yeah. I mean, there are also instances of it. I mean, it as I said, it's sort of, you get this thing where it comes up in the here where K was the unique extension of this restriction, but it's like, but not definable over the n plus 2, and you know, you don't get it in L of this here in this situation that I'm thinking about here. You know, there's also a very analogous stuff that happens in a model theory where you can have, you know, M1 that the minimum model for one wooden cardinal, and it computes, you know, how to iterate itself. So it knows sort of certain elementary embeddings on itself up to a certain point, but then there's certain ones that it can't compute. But those ones are also unique on the outside, and you can add them to it in, you know, in the appropriate way. You can, certain ones you can add to it, and then when you add it to it, it's like it's such canonical information that it sort of doesn't damage the universe significantly when you add it, and it has nice properties once you add it as well. And so yeah, so that would sort of be an instance of that, where on the outside you can see this unique object and you can add it, and in this case that it also, like, you know, when you added it, the resulting universe has very nice properties and so forth. So yeah, that is one case of that sort of thing.
Mm-hmm.
But that, you know, basically there you're just adding, there's elementary embeddings as well. So yeah, there's sort of canonical elementary embeddings that you're adding to the model.
Right. I guess I was just thinking that maybe if one does something like that, I'm just thinking about this problem with not having a hierarchy on the stuff that gets in V lambda plus 2, something like that. Like if you are careful in what you add, maybe it's not V lambda plus 2 that you would consider, but somehow, you know, the previous stage enriched by everything that is unique over the previous level or something like that, that you come up with something that is more amenable to finding some kind of hierarchy, or I don't know. It's just a very vague idea.
Yeah, I mean, there's also, you know, you know, Hugh has done, you know, proved lots of analog between LV lambda plus 1 and determinacy, and then Gabe used some of this periodicity stuff to extend that to higher levels, and you know, so maybe there's more in his work that would help there in both of their work that would help there. But there's also the analogy here. Under determinacy, we get the hierarchy of the sets of reals under the wage complexity. So that sort of thing could also have analogs here in for v lambda plus 2, v lambda plus 1 replacing the reals and v lambda plus 2 replacing the power set of reals.
Yeah. Great. Any further questions or comments? Okay, I think let's just thank Farmer again for this very interesting talk. Thanks a lot.
No worries. Thanks.
Yeah, thanks, Farmer.